Hi guys, it's your guy Olumide, and today we're gonna be solving another one of the most commonly asked tech interview question, the minimum coin combination. It's a DSA problem that is commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Microsoft, Apple, and other top tech companies. The problem statement states that you are given an array of coin values and a target amount of money. Return the minimum number of coins needed to total the target amount. If this isn't possible, return -1. You may also assume that there is an unlimited supply of each coin. So here, what the problem statement is trying to tell us is that we're going to be given an array of coin values, and then we want to find the minimum amount or minimum number of coin that is going to total the target that will be given to us. So we are given a target 5, and we are given this coin values 1 2 3. So we want to find the minimum number of coins that's gonna total 5, not less than, not greater than, but that will sum exactly up to 5. So if it isn't possible, we are asked to return -1, right? So let's see, looking at this now, we say that there are 2 coins. If we are very efficient with summing this each of this coin, don't forget we can actually have an unlimited supply of each coin. So meaning that but if we are efficient enough, we know that adding a 2 with a 3 is gonna give us 5, and that is the minimum number of coin that we need to total this 5, right? Even though we can have 1 5 times. Why? Because the problem statement told us that there is unlimited supply of each coin. So we could have a 1 and another 1 and another 1 up to 5. We could have a 2 and another 2 and another 1, which will sum up to 5. We can have a 3 and another 1 which is sum up to 5, right? But because we are after the minimum possible number of coin that is going to total this target, we are going to be using a 2 and a 3. So this is what that's what the explanation is trying to tell us here. Let's consider this other example here, right, whereby we are given the coin values of 2 and 4, and we are given this target of 5. You see that there's no way we want to sum up these coin values that we make up 5, right? It's gonna be greater than 5 because 2 plus 4 gives us 6, which is greater than 5, and there's no way each individual coin want to make up a 5. 2 is less than 5, 4 is less than 5. So because of that, there's no coin combination, there's no number of coin combination that is gonna result in this total. So because of that, we return -1, just as the problem statement states. To solve this problem, we could have tried a brute force or use a brute force solution that requires trying every possible number of coin combination, right? So consider this particular example here whereby we have 1 2 3. So we are going to try every possible combination, trying 1 2, trying 2 3, trying 1 3, and all possible combination, and then going after the one that actually require the minimum number of coin to give us the total target, right? But we can't use that brute force here because we can have an unlimited number or supply of each coin. So we can have unlimited possible combination of coin, meaning that we could have 1 5 times, we can have it 10 20 times, because we can use it again and again, right? We have unlimited supply. So because of that, we need to find a more efficient way to solve this problem. Consider this example below where we have a coin array of coin 1, coin 2, and coin 3, and a target of 5, right? So if we use the coin 3, or let me say if we use coin $3, right, then we need a coin $2 to make 5, right? Because when we use a coin $3, the target is reduced to 2, right? So meaning that we need a coin $2 to make 5. Now this means that we actually have reduced the problem from a target of 5 to a target of 2, right? And meaning that now what we are requesting is the minimum or fewest number of coin that is needed to make the target 2. Why? Because initially the target was 5, but by using a coin 3, we reduce the target to 2, and now we are going to find the minimum number of coins that will give us the target 2. So and this indicates that what, in finding the solution to the main problem, there exists some subproblem. So and we can find the solution to the main problem through this subproblem. And what's the subproblem? The subproblem involve finding fewer number of coin to make a smaller target, right? Because the target is initially 5, and by using 3 the target gets reduced to 2, and now we just need to find the minimum number of coin that is required to make up a target of 2, right? And by that we just add that minimum number by we add 1 to it, right? That one represents the coin 3 that we use here. So and what I'm just trying to say is that what it actually means is that, considering this target 5, by using coin 1, don't forget that we have this array of coin 1 2 3, right? By using coin 1 we got our target reduced to 4, right? If that we use coin 2, we get it reduced to 3, and if we use coin 3, we get it reduced to 2. Now on a more broader view, this is what it looked like. So by using coin 1, it reduced to 4. Again, we can decide to use coin 1, which will reduce to 3, and we can decide to just continue using it on and on like that. Why? Because we actually have an infinite number of each coin, right? So but by using coin 2, we have our target reduced to 3, and what we are left with now is the minimum number of coin that will give us this target of 3. So we can actually use 1, we can use 2, and we can use 3 to find this minimum number, right? So and by using 1, 1 minus 3 minus 1 is gonna give us we are gonna be left with finding a target of 2, right? So it's a target of 2, and by using 2 we are gonna be left with a target of 1, and by using 3 we are gonna be left with a target of 0, right? So now we see that these parts whereby we for a target of 5, which is the main problem, we use 2 to give us a target of 3, then we use a 3 to give us a target of 0, actually leads to 0, right? Meaning that it actually sum up to the minimum number of coin. It actually sum up to the target, right? So similarly, if you look at this part also, whereby we use 3, we have a target of 2, and by using 2 we are gonna be ending up with a target of 0, meaning that what, this also sum up to the target that we are finding. So now, since at each point, to find the solution to the main problem, that is the minimum number of coin that we sum up to this target 5, since we are trying to use 1 and trying to use 2 and trying to use 3, then it means that the solution will be the one that actually gives us the minimum number of coin between these 3 parts. So meaning that after finding the minimum number of parts, the minimum number of coin that will give us this target 4, right? And then after finding the minimum number of coin that's gonna give us target 3, then the minimum number of coin that's going to give us target 2. After finding them, right, is gonna the minimum number of coin that is gonna give us the main problem, which is target 5, is going to be 1 plus the minimum number of, it's going to be, let me just use literal English now, it's going to be the minimum number. Okay, let's say that in getting target 4, it gives us 3. It gives us, let's say that by following this part now, right here, the minimum number of coin that is needed to make this target 4. Don't forget that target 5 is the original problem. Then we break it down into sub problems by using coin 1, and by using coin 1 it will reduce the target to 4, right? And if we use 2, it's gonna reduce the target to 3, and if we use 3, it's gonna reduce the target to 2. Now we are gonna find the minimum number of coin that will make up each of these sub problems, right? So don't forget that there are sub problems because they're actually gotten and derived from the original problem, so they are actually reduced. That's why we call them sub problem, the reduced problem, because at each point we have used a particular coin to make up a smaller target. So after getting the minimum number of coin that work for that will make up target 4 and target 3 and target 2, definitely to get the original solution, because the original solution is just going to be a number, right? A minimum number. So we have 3 minimums, right? The one for target 4, for target 3 and for target 2. Now what we are interested is the minimum between these minimum numbers, right? Meaning that the minimum number that is actually derived from target 4 and then target 3 and target 2, we are going to look at the one that is smallest among them, because we are after the fewest number of coin, the minimum number of coin. So anyone that is minimum, we are just going to add 1 with it, and that one actually represents the coin that we use to create these problems. Don't forget that if we have a value returned there, then we have to add 1 to it. So because we actually use a coin 1 to create this problem, similarly we use a coin 2, which is still 1 coin, right, to create this problem. We use coin 3 here, which is still 1 coin. It's just coin $3, coin $2, and coin $1, but it's still a single coin, right? So, and then that's how we derive the problem now. So we call this problem that's how we derive the formula. We used to call the formula recursion relation. So it actually relates the subproblem and the main problem together, right? So the minimum coin combination for a particular target, say that the main target here, the main target target 5 is equals to 1 plus let me do it this way. Let's do it this way, so it's gonna be distinctive. So it's equals to 1 plus the minimum between the whole minimum coin combination of target minus coin for each coin in coins. So don't mind this formula that you are seeing here. All it's just trying to say is that for all combination, for all sub problem that we can get from a problem, say that the main problem 5 now, we can get some sub problem. By using 1 we get this sub problem, by using 2 we get this sub problem, and by using 3 we get this third sub problem here, right? So now for all of this sub problem, we just have to find the minimum between each of them, that is the one that takes the minimum number to get to get to the target, right? So, and then after that we add 1 to it, where the 1 represents the actual coin that is used to create these sub problems, right? So, and that is how to solve this problem. Now naturally we need the base case to solve this problem. A base case is actually a case whereby when we get to a we are going to traverse this tree now, and when we get to a point in the tree, we need to stop traversing, at least for that particular part. Imagine by taking this part and then getting this problem by using the coin 2, we get this problem, and by using the coin 3 we get this problem. We don't want to keep on going on and subtracting, or otherwise we're going to be having a minus, right? We've gotten to 0 already, so we don't need a minus. 0 actually indicates that that this part, or let me say this number of coin combination, actually sum up to their targets, whatsoever the target could be. So, and because of that, whenever we come across a 0, that is our base case, we return 0. Now why do we return 0? Why? Because by using a coin, right, we actually consider this 0 here, target to be 0 here, right? By using the coin 3 for this target 3 is what gives us 0. Why? Because 3 minus 3 gives us 0. So that means that actually coins 3, that single coin combination is enough to make up the target, right? Because it's 3. So, and 3 is equals to 3, right? So when we try to subtract 3 from 3, it gives us 0. And because of that, we want to return 0. And why I return 0 is because when we return 0, we will add that 0 with this 1, with this coin that we use here. We use one coin here, so it will make up 1, meaning that 1 plus 0, right, which makes up 1. And that means that just a single coin combination, just a single coin, which is coin 3, makes up the target 3. So this thing is logical, right? So similarly, look at this 0 here now, this other 0 here. So we know that we have a target. We don't know actually, but we have a target of 2. It's an algorithm, but I'm trying to put the logic here so that you understand. So this is how it's gonna be looked, and this is how it's gonna happen too, but in code, right? So we have a target of 2 here, and now we have the target of 2 is by using the coin 3 on the target 5. So 5 minus 3 gives us 2, meaning that we just have we just need the number of coins that is gonna make up 2, right? So because we have used 3 on 5, so we have 2 left, and by using 2 again on 2, we have a target of 0. Why? Because 2 minus 2 is 0, right? That coin alone is enough to make up the target, and because of that we return 0. Why? Because by returning 0, we are going to add it up with this particular coin that we use, so and that's gonna make up 1, right? Meaning that what we just that way we make use of just 1 coin to sum up these targets, and then after we have 1 here, we are gonna return 1 plus 1 again. Why? Because we are going back to this target up here, right? So because 1 coin have been used to make up this target 2, we are gonna add 1 again to that coin to make up 2. So meaning that 2 coin is actually used to reach this target 5. Why we add another 1 is because we use 3, right, to make up this target 2, and we use 2 to make up this target 0. So summing it up like that is gonna give us 2. The first one that is used to make up target 2, and the other one that is used to make up target 5. So, and that's why you can see 1 here. So that is the reason for 1. It's actually, that one represents the particular coin that is used to make up those problems that you can see. So that's how we solve this problem. So now let's talk about the concept of memoization now. So memoization is actually a term that is used in dynamic programming, right? And what it does is that, first of all, look at this problem here. You will see that there are some problems that are repeatedly solved, right? Look, we've seen this problem, target equals to 3 here. So, and what is literally mean is that it's actually a sub problem, right? It actually means that, find the fewest number of coin that's gonna sum up to the target 3. Similarly, as you can see here too, it's trying to tell us that find the fewest number of coin that's gonna sum up to target 3. So definitely it's not gonna change. It's the same sub problem of target equals to 3. So the fewest number that the algorithm is going to return for this is the same is going to return for this right here, and in fact it's the same that is going to return for this. So it's just mere repetitions of already solved problem, and that's what memorization handles. So it means that anytime we have solved the problem before, we really need to store it, so that any other time we come across the problem, we don't have to solve it again. Imagine we are not dealing with target of 3. Imagine we are dealing with target of 3 million. Imagine it, we have to traverse down to 0, and then recursively go back again to 3, right? So imagine doing that for each and every for multiple times. It's gonna lead to a lot of inefficiencies, right? So because of that, anytime we've solved the problem, we are gonna do what? Add it to a hash set, right? And then we are gonna add it as, let's use a hash map, so that it will be a key value pair, right? So a hash map that will be a key value pair, so that we can know the key. So and what will the key be? The key will be the target. At this point, for this one now, the target is 3, so we make the key 3, and the value will be the already solved. It has to be solved once. After solved once, anyone that come again wants to use that saved value. So let's say that the value is 4, right? So this is how the key value pair is gonna be, right? So that anytime it's come across that target again, we're just gonna check into the hash map in 01 time, constant time. We're gonna look up into the hash map and try to check, does this have we solved this thing before? If we have solved it, we just return the value instead of having to solve it on and on again. So simply we are just gonna be using a hash map to do that. So, and that's how we solve this problem. So we are gonna be going to the code implementation, right? And stay tuned. Alright, let's go into the code implementation for the minimum coin combination, right? So we are having this function minimum coin combination, and it's gonna be taking in some parameters which are actually the coin values, right, and the target. So this is the coin values here, so which is a list of integer, right? So and then the target, so which is actually an integer, right? So now let's go on to solve this problem. First of all, let's define the minimum coin. We are asked to return the minimum coin that we sum up to that target. So we are gonna be setting the minimum coin first of all to we are gonna be setting it to an infinite number. So okay, let's place the return for this function. The return will be an integer, right? Because we are returning the minimum coin combination, or minimum number of coin combination. So this minimum coin variable is going to help us to keep track of the minimum number of coin combination, and we are setting it to an infinitely large number. Why? Because first of all, we want it to be large so that when it's trying to compare with other number, is always going to be that number. You know, no number can be greater than infinity, right? So we are always sure that the first number we are going to compare this minimum coin with. Why? Because we are going to be comparing it with minimum with the minimum number of combination from each branches. What I'm trying to say is that don't forget that, like I explained in the logic, we will be having this target, and from this target, by using one coin, by using each of the coin in this coin array, we are going to be creating sub problems, whereby the sub problem involve finding the minimum number of coin to make up a smaller target. By using the coin, we come across a smaller target, and then that's just a sub problem. Why? Because we also want to find the minimum number of coin that's gonna sum up to that smaller target. So meaning that frequently we will be finding the minimum, right? So, and then to be on the safe side, we are placing it to infinity at first. I mean the minimum coin variable. Alright, so now for coin in coins, right? And what this for coin in coin means is that we have to iterate through each of the coin. Don't forget that each of these coin actually represents sub problems. Why? Because by using each of this coin now, we are gonna create a smaller target, right? Which the target is going to be the original target minus coin. You understand? So okay, remember from the logic I talked about using having the target of 5, and then and one of the coins are 1, the other is 2, the other is 3, right? So by using 1 on 5, we'll come across a smaller target 4. By using 2 on 5, we come across a smaller target 3, and by using 3 on 5, we come across a smaller target 2. So we are going to be using each of these coins to bring about a smaller target. That is if the target is actually greater than or equals to the coin. We don't want a scenario whereby we'll be dealing with minus, right? So we want it to be greater than or equal to it. So don't forget, if it's equal to it, we still want that. So why? Because at that point it's gonna make up 0, and we are after 0 in fact. So and what we wanna do is that minimum coin, so if it really is if it's greater than or equals to target, the minimum coin equals to the minimum between minimum coin and 1 plus DFS of target minus coin, comma coins, comma target. Okay. So well, you might be like, why did I get all of this idea from? So it's also part of the logic like that I explained. So because this minimum coin is what we are going to be returning, right? So we need to make sure that it's keeping track of the minimum coin indeed. So whenever we create a minimum coin, we find the minimum coin, we always want to find the one that is minimum to it. So that's why I'm trying to compare the previous minimum coin with a new minimum coin for each coin in the coin variable, right? So that's what it simply means. So I'm trying to keep track of the minimum coin, and then 1 plus DFS of target minus coin, comma coins is that don't forget from the problem logic, what actually is happening is that from the logic, right, you will see that we have this diagram. Let me show you the logic right now. Look at the logic now. We use 1, we use 2, and we use 3. That is what is represented in this problem. Let me show you the problem as well. Oh, let me show you this. Sorry. So you will see that I'm saying that I said for coin in coins. So that is what you can see on the logic here, on the logic table here. So you see that I use 1, 2, and 3. That's what for coin in coin mean, whereby 1, 2, and 3 are actually the coin values, right? So now for each of these 1, 2, and 3, we still want to find the same thing. What is it? We want to find the total number or the minimum number, the minimum number of coin that is necessary and needed to sum up this one. So that's why it looks like I'm calling the function again. I'm calling that DFS function. So this DFS function is what is going to help us to find this DFS function here is what is going to help us to find the total number, the minimum number of coins that is going to make up that smaller target that we just create. And what's the smaller target? The smaller target is target minus coin, right? That's the sub problem. So, and then after that we just simply return minimum coin, having it in mind that minimum coin at this point will really be the minimum out of all these sub problems. So now let's create the function DFS, right? So I'm going to be collecting the target. So this target will be the smaller target. Don't forget that this target is actually target minus coin, provided that coin is greater than or equals to target. So that's what we are collecting here. So let me even put it as an integer. And then I'll be having coins, COINS, which is actually a list of integer, right? So, and the return of this should be an integer, because this is going to return the minimum number of coin that is required to make up that smaller target. So first thing is that if the target is a 0, what did I say that we are gonna do? I said we are gonna return 0, because that way we found the target, right? We find it's actually a sum up to 0, right? So otherwise what we want to do is that we just want to iterate through the coin. So for coin in coins, so that we are gonna find we are gonna iterate through and try to find sub problems. I mean, we are gonna be using each of this coin to create a new target, so until we make sure that the target becomes 0 or become less than 0. So in a situation where it becomes less than 0, we are not going to do anything. That's why I put this condition there, that if target is greater than equals to 0, is greater than equals to coin. So why? Because once the target become less than coin, then target minus coin is going to give us a negative answer, and then there's now a negative answer. It's like you are finding you are finding 5 and you are giving a coin value of 2 and 4, so it's not going to make up 5. So it has to be 0. It must not be greater than, it must not be less than 0. So if that is greater than equals to coin, then we are also going to be keeping track of a minimum coin, and because of that I'm going to define the minimum coin here. Don't forget that the essence of this DFS function is to return the minimum coin for each of the sub problems. So we're going to set it also to float of infinity, and then so if target is greater than coin, they want to evaluate the minimum coin and say that the minimum between it and that is the, want to just keep track of the minimum coin, and then DFS of target minus coin, comma coin, right? So, and after that, for this particular DFS function that is called, it will be called on each of the let me just say simply that it will be called on each coin, each of the sub problem. So each coin here, 1, 2 and 3. So, and for each of them we just want to return the minimum coin. So by doing that, now this one is going to collect that value, and then it's going to add it with 1, right? We are going to add 1 here as well. So this one will represent the particular coin that we use, right? The particular coin that we use to create this sub problem DFS here. So, and that's how we solve this problem. Let's run it and see how it goes, please. And I really hope you understand this. I really hope you do understand it. Alright, so we have to return there, which is actually correct. Why? Because a coin combination of 2 and 3, I mean coin 2 and coin 3, will make up 5, and that's just 2 coin, right? So I do hope you understand this problem. I really do hope you understand it, and if you do, kindly like, follow and subscribe to my YouTube channel also comment on under this post, right, that you do understand it. Thank you. If you don't understand it, don't worry, it could be a little bit complex, right, but the one that is coming, my subsequent videos, won't be complex as this. And also go and check out my previous video. I've done a couple of video on my YouTube channel and across my social media platforms, so do check these ones out, but do well to subscribe to my YouTube channel. Thank you.